Many of you will have come across artificial intelligence through the movies. It's been depicted in many different movies, and I would say also not in an overly positive light. The AI is almost always the bad guy in the movies. There's been a lot of interest in AI in recent times, and a number of famous people have made some very strong and striking predictions about AI. So Stephen Hawking said, the development of full AI could spell the end of the human race. Elon Musk, AI is our biggest existential threat. And so what I want to do today is to talk a bit about the reality behind this, so to get away from the movies and to get away from the hype, and tell you what AI is like today. So many of you will have interacted with AI systems already today. So if you've spoken to your phone on devices like Siri, or devices that you have in your home, then you've interacted with AI. If you've bought a movie or you've bought something online, then you will have interacted with AI. It will have made recommendations for you. If you've played computer games, many of these smart characters in these games use AI technologies. You may have AI technologies in your home if you have something like a Nest thermostat that learns your pattern of usage of the home, when you're there, when you're not there. And if you've bought something from Amazon, which I think probably covers the rest of you, then Amazon extensively uses AI in its robotics, in its warehouses to make sure that the delivery of packages is very efficient. So, as I say, what I want to do is I want to talk about what is AI, first of all. So my definition, or a well-used definition, is that AI is an activity devoted to making machines intelligent, where intelligence is the quality that enables an entity to function appropriately and with foresight in its environment. So that's a standard definition of AI. It's been around for 20 or so, 30 years now. Much of what current research goes on in this area is focused on systems that are specialized for particular tasks. And all the AI examples that I'm going to give you and talk about are focused on particular tasks. But there are those in the field who focus and his aim is concerned with artificial general intelligence. And so that's like the AI of the movies. That's the things that all the movies are about. So a program, a robot that is able to function much as we are in society and can act and interact across a whole range of activities. Okay, so there's a difference between specialized and general AI. Now, although AI is currently a very popular field, which is great why so many of you have spent your Friday evening here, AI is not a new field. So Alan Turing in the 1950s published a paper, an amazingly prescient paper, like much of his work, called Computing Machinery and Intelligence. And this paper set out to ask the question, can a machine think? And what he did, instead of asking that question directly, he replaced it with an alternate question, which he thought was the same and the equivalent. So his particular question he posed is, could a machine playing a question-answer game fool a human into thinking it was not a machine? And that's what has latterly become known as the Turing test. So if you've seen the movie about it, you will know, you will have come across it. It's behind a computer, behind a screen, and you interact with a device that may or may not be human, and you have to try and figure out whether the thing that you're interacting with is in fact a human or is a machine. And if you can get a machine to fool people into thinking that actually it's a human, then that's a way of passing the Turing test. So in his paper in the 1950s that laid this out, he constructed a series of arguments and absolutely believed that this was possible. So he absolutely believed that artificial intelligence was possible. The specific term, artificial intelligence, was coined by US computer pioneer John McCarthy at a conference in 1956. So this is not a new field. Now, in its long history, there have been a number of spectacular landmarks in AI, and I just want to talk you through some of those. So I think the first real one that really caught people's attention about this field was in 1997, when IBM constructed a program called Deep Blue that beat Garry Kasparov, the world chess champion. So in 1997, an AI program, a narrow AI program, all it can do is play chess, beat the world champion. Then, a number of years later, IBM, they quite like going for these big challenges, constructed Watson, which played a quiz show in the US called Jeopardy. And actually, we're going to come back to this, and I'm going to show you actually how Watson played Jeopardy later on. So I'm not going to say very much more about that. Recently, last year, there was a lot of excitement as DeepMind, AlphaGo, beat the reigning European Go champion. And that's really exciting because Go is such a more complicated game than chess. So chess is a complicated game. It's got lots of possible moves, but AlphaGo and playing Go is a very much bigger, more complex set of possibilities. So there are more potential moves in Go than there are particles in the universe. Okay, so that's a big number, all right? So, and in contrast to Deep Blue was a very impressive engineering feat, but actually what it did was it essentially was able to look at almost all possibilities, which in computer science we would call a brute force solution. So it looked at all possible moves and could then pick the best one. You can't do that with current computers for Go because it's so much bigger, it's so much more a complicated game to be able to play. And then earlier this year, there was a program, a competition to play poker, and an AI program beat a series of poker professionals over a weekend. And what's different and interesting, particularly about the poker game, is actually you have incomplete information. So when you play Go, it's a very complicated game, lots of possible moves, but you know exactly where the board is. There's no doubt that these are the counters on the board, that the counters are on this square, that this one is black and that's white. And so sort of that's a complex game, but it's a game of complete information. You can see everything that's on the board. Obviously, when you're playing poker, you do not have complete information. You have information about what cards you have, but you don't know what cards your opponent has, and you don't know what cards have not yet been played. And so it's, again, a very complicated game. So as I've alluded to, AI is something that's been around since the 1950s. And so sort of why you might be asking and wondering, why is AI so popular? And I've put in brackets again. I've been an AI researcher for 30 years now. And during my time, what I've experienced is that AI has been really, really important. AI is rubbish and has failed and we shouldn't be doing it anymore. And we've sort of had a number of those cycles in my time. Generally, I prefer the peaks to the troughs. And at the moment, we're clearly at a peak. And I think we're at a peak of interest for a number of different reasons. So firstly is the abundance of processing power. So it's much cheaper and easier to have very much more powerful computers now. So, there's the statistic that sort of we have more computing power in our iPhone than man had at his disposal when he went to the moon. So the computing has got very, very much more powerful. And that lets you process much more data and much more information. And so you're able to do complicated things much quicker and very much more often. So cheap processing power is really important to that. A second key aspect is the amount of data that we're generating. So we have a huge number of connected devices, so iPhones, other devices that have lots of information. We have more connected devices than there are people on the planet, and that will, that's something that's going to continue to grow over time. So lots of sensors in us, on us, at our work, at our home, and that's generating ever more amounts of data. And so, again, there's some really interesting statistics about that. That's in the yellow box up there. So there's a calculation about all the words that have been ever spoken by human beings. And so if you convert that into information, you end up with a number of 5 exabytes. That's just a lot, as you might imagine. All the words human beings have ever spoken is quite a lot. You might debate how they calculate that number, but let's assume that's right. Actually, so there was more internet traffic last year than there has been in terms of words ever spoken. So it's really getting masses and masses of information. And this, for me, is sort of the driver for AI. And so my take and my reason why I think AI is so important is that humans alone cannot hope to process the volumes of data that are necessary to make informed decisions. There is so much data coming at us. We need assistance, and my contention is that we need artificial intelligence. However, machines alone can rarely do all of a complex activity. I think there will always be activities that humans are best at. And so for me, building effective partnerships between humans and machines is the key aspect of what this research and what this area should be about. And this involves partnerships I've deliberately chosen the word partner. So moving away from humans being the master and technology the slave. That's how we're used to interacting with computers. We're used to, in general, instructing computers and them doing what we want. And so I think that's going to change. I think it will very much become a partnership model where we're working alongside in a peer-based structure with machines. And I'm going to give you some examples of where that's the case. And I think that recognizes that complementarity, and that partnership recognizes the different expertise and roles that gets played in these systems. So that's what I think of when I think of AI. So now you all understand it and absolutely clear on what AI is. Let me talk a bit more about how we build an AI system. So what we have is, so you can think of an AI system, let's just think of it as a program, which is what it is. Okay, so there's nothing elaborate, there's nothing magical about an AI system. It's a computer program. It's connected to some environment, and so the environment will depend on what you are. If you're playing chess, it's the chessboard, and there are various sensors and that are able to understand what's going on, which chess pieces are where, and there are various effectors which can change that, so they can move the pieces from one to the other. In between sensing and acting is some decision-making process, some decision-making activity. And that's where AI researchers and AI systems, that's where you build your capabilities. So that might involve making some predictions. So if I move this chess piece from here to here, I might be able to predict what the outcome would be. I might be able to predict if that would put the opponent in check or if that would let the opponent take that piece. So we might do some predictions about what would happen from different moves. Those different moves might have different expected rewards. So we might be able to perceive this if we can take an opponent's piece. That might be a good thing to be able to do. And so the expected reward of that action would be quite high. Losing a piece might give you a lower expected reward. And so you have some idea about what the expected reward is, and then you have to determine from those possible actions that are worth different rewards, which action you actually are going to take. Now, to do all of those things, you may include the program's knowledge about the world, about actions, and some preferences. So that's what's inside an AI system. And they will have those components to bigger or smaller extents depending on the applications. And I'm going to show you some of those applications in a moment. So to do those things, we have to overcome a number of scientific challenges. This is what AI researchers spend their time doing, solving these sorts of problems. And none of these are solved problems yet. We have partial answers that work in some cases, but we haven't closed the book on any of these. So the first of these is, how do you represent knowledge? How do you represent knowledge about the world, much of which may be uncertain? Okay, so when you're playing a game of chess, for example, actually if you move there, you might not know exactly if that's a fantastic move or that's a less fantastic move. Okay, so you have some knowledge. Some of that will be uncertain. How do you decide what action to take? Remember, go, more possible actions than particles in the universe. So how, out of those myriad of possibilities that you can make at any one time, do you decide actually which one you're going to do next? So how do you explore those? It's a massive search space to look over. How do you figure out which one to do? How do you encode preferences? How do you know which is good moves and which are bad moves? And how do you construct a plan of action? So that might not just be one action, that might be a series of actions that you need to be able to take to get to where you want to be able to do. How do you learn from past experiences? So if you've made a particular move in the past and you got a lot of reward, how do you learn that that might be a good thing to do again? Of course, it might not always be a good thing to do again. And how do you interact? So how do you communicate and coordinate both with people that you're interacting with and other AI systems? There might not just be one AI system in the environment. And so what I want to now be able to do is to talk through some examples where you see different aspects of those things. So I've outlined what the challenges are, and I want now to sort of give you a feel for the kinds of technologies and the kinds of methods that AI uses. And sort of a nice first example, I think, is about AI making recommendations. So recommendations, you will all have seen these if you go to movie sites or if you go to shopping sites. You will see, sentiments like, people like you like these, or this might be interesting, or you might be interested in this film, you might be interested in buying that. So what's behind that is some of this technology that I'm going to talk about. I'm going to do it in the context of film recommendations, but it's the same for any other good. So what you might have is a series of films in your database, so films 1 to N, and then you might have a series of users who've rated some of those films. So some of them they might like, so those would be those with the green ticks. Some of them they might not like, which would be those with the red crosses, and some of them they might not have expressed an opinion on. Okay, so that's the knowledge. We spoke about encoding the knowledge, so that's the knowledge that we have from a number of users. And then when a new user comes in, or a user starts interacting with this, then what the problem, the AI problem, is to try and figure out what user that you already have in your database, or what set of users are you, the person who's using the system right now, most like. Okay, so that's how these things work. And there won't be someone in the database in general who likes exactly what you like and dislikes exactly what you like and is indifferent about all of those things. And so you have to do a match. So you've got partial information, and you have to try and figure out which of those people, which of the recommendations that you like. And as I said, it might not just be one person you might be like. You might kind of be a mixture of user 2 and user 4 and user 6 in some way. Okay, so I'm going to give a demonstration now, which is developed by Microsoft Research and Chris Bishop, who's sitting here in the audience. So I hope I get it right, Chris. Okay, so here we have a collection of films, as some of which you may recognize, some of which you may not. And at the moment, they're just randomly scattered around between the green and the red. Okay, so there's nothing significant to that. What I'm going to do shortly is start moving some of those films around, and you'll see how the system will start to try and classify those things. So things that are in the green are things that I like, or I might get a member of the audience to like, depending on how it goes. And then things in the red are things that we dislike. Okay, so what you'll see is you'll see the films move around. So the way in which they move up and down the screen is irrelevant. Okay, so ignore that. That's just, you have to be able to place them up on the screen. You will see them move from left to right, and sort of those that migrate towards the green are those that the system is predicting that are consistent with liking those, and those that move towards the red are those that the machine doesn't like. So I think I'm going to try a demo on this. So in typical Royal Institution form, so can I have a volunteer who's willing to express their film preferences? Who I can see. Yeah, so gentleman up there in green. Do you just want to come down a bit? I hope you have decent film recommendations. So would you like to identify from the screen a couple of films that you can see up there that you like?
Matrix Reloaded.
So where can I, and you might have to point to me at them as well.
It's behind your,
Yeah. Which, I'm going to need glasses as well for this. It's terrible when you get to a certain age. That one?
No, the one.
That one. Okay, so we like that one.
We love that one.
Okay, so previously they were just randomly scattered around. Now it's kind of a bit uncertain, but there are some that are slightly more towards one side than another. Do you want to pick another one you like?
American Beauty.
That one up there?
Yeah.
Okay. Right, so after just a couple of thoughts here, so now it's starting to make some predictions about things that you like. I'm hoping you like some of those on that side. Otherwise, I'm blaming Microsoft. And maybe some you don't like. So do you want to pick one that you don't like?
Oh, one I really, really dislike?
Yeah.
Oh my goodness, such a...
So many possibilities.
I know, right? What is the genuine worst here? You know what? The Wedding Planner. I mean, it's just...
Yeah.
Doesn't get
Okay.
worse than that.
Thank you. That's probably what I needed. So can we give a round of applause? And so what we have here is sort of, it's learnt the profile and sort of started to pull those things apart. And so when you make those sorts of recommendations, if you pick one that sort of confirms, I might imagine you might like Reservoir Dogs out of that lot. Actually, the amount of change in the system is not very much, because it's sort of you're confirming many of the hypotheses and things that are consistent with it, and probably the same with Pulp Fiction. Okay, so when you make those moves, you don't see very much in the way of information changing. Now, what happens? You may or may not believe this, and I'm sorry to do you this injustice, but I'm going to take The Nutty Professor, which I'm guessing you may not be your favorite film, and we're going to see what happens when something that's well over here, so well over on this side, The Nutty Professor, actually you declared that you liked The Nutty Professor in a bad moment. And you see how that really changed things. Okay, so sort of when you made consistent predictions and you were doing consistent things, not very much moved around the screen. But actually when you did something surprising, you declared a love for Eddie Murphy and The Nutty Professor, then that changed things a lot. Okay, so sort of that's how these sorts of systems work and operate. It's learning the sorts of person that you are, who you are like, and then sort of making predictions based upon that. Okay, so I said I would talk a bit about Watson. So this is an American game show. If you're American, you will absolutely know it. And this was chosen as a challenge because actually it's not just sort of recalling facts. It's not a mastermind type thing where you're given a question and you have to determine facts. The questions, as you'll see, are quite complicated and sophisticated in the way that they work. So let's just see how this works. And so this was a really tough competition. So the two humans playing this were the best Jeopardy players ever. So they sort of brought back throughout the however many decades Jeopardy has been going, they brought back the two best humans. So it's having to understand that question, figure out what the answer might be, figure out how certain it is in that answer, and then buzz in all of that. And that's real time, okay? So that's the time it's operating. So it's doing that against, as I say, the best human Jeopardy players ever. So let's see how it goes about doing that. So we're going to take the category here is Michigan Mania, and the clue was in 1894. C.W. Post created his warm cereal drink Postum in this Michigan city. So that's what is fed in to Watson. And so the first thing that it has to be able to do is to make sense of what has just been said to it. So it has to understand the question. So what it constructs is a graph of all the key concepts that are in there. So you'll see drink, Postum, created, cereal, warm, Michigan, city. So those are the sorts of concepts that it can understand from that question. And it's figured out what are the key words. So it's constructed some of those from that sentence. And it's also done something that they call LAT detection, which is lexical analysis type. And essentially what that is it's trying to figure out what sort of thing the answer is. And so the sort of thing that you will all know instantly, even if you don't know what the answer is that the answer is going to be a city. So it's going to be a town. It's not a person name. It's not a monument. It's going to be a city name. But the machine has to figure that out. And actually, that bit is exceedingly hard for a machine to be able to do. Okay, so it's done some question analysis. So then, having worked out what the questions are, so it knows it's looking for something that's a city in Michigan, it starts searching. So searching in the normal way that you're used to interacting with a search engine on things like Google. So it has ingested many, many information sources, the key ones of which are Wikipedia and a number of others, but it has Wikipedia inside it. And so what it then does, it's doing a search over all these many different sources from those keywords that it's extracted. Okay, so it used the keywords to search millions of documents to find the kind of relevant things that are appropriate to that. So that's its primary search. So having done that, it then wants to start coming up with some hypotheses as to what the answer might be. So it goes through a hypothesis generation phase. So candidate answers are identified in the research results, so looking at things like the titles of documents and also sort of text in the document, so named entities, noun phrases, dates, etc. And then sort of it's starting to build a table. Remember I spoke about how you represent knowledge, so it's starting to construct a table of things that are potential candidate answers. It's constructing things that might be the answer to that based on the documents that it's got. So it then, having got a series of candidate answers, goes through a hypothesis and evidence scoring phase. So it has a series of small programs or rules, you can think of them as, that sort of help it try and refine and distinguish between those many candidate answers. So one is the geo rule, if you like, which checks that the correct answer is a city spatially located within the state of Michigan. So we know from our analysis of what type the answer is that it's meant to be a city and it should be in Michigan. So your answer should be consistent with that. And you will see that some of the candidate answers, like 1895, doesn't pass the test of being a spatially located in the state of Michigan. So that gets quite a low score from that particular set of rule. Another rule, TICOR, estimates the likelihood that the candidate answer is of the correct type. So, is it a city? And again, sort of the candidate answer 1895 is not a city, and so it's able to sort of give that quite a low score. So it has a series of these sort of rules that it applies over the answers. It then, sort of having done hypothesis scoring and evidence scoring, does some confidence merging and ranking. And so it starts to pull all of that together. So it detects variants of the same answer written differently or shortenings of those things to come up with the answer. And sort of it's able to compute, depending on the sorts of evidence that it has, how confident it is in that answer. And so that's how this works. So when you see it, you think, wow, that is amazing. That must be real artificial intelligence. And actually, when you start to unpack and you start to dig underneath it, actually you think, well, it's very impressive. It's absolutely really impressive. But, is this what we mean by artificial intelligence? It's searching, it's doing clever things, it's well engineered. Just to give you some hope for humanity at this point. So, as I say, that's a bit of hope for humanity there. So it's given clearly the wrong answer, right? So it's given Toronto, it should have been given a US city, it's given entirely the wrong answer. It knew it wasn't very certain about this, which is why it didn't invest very much money in it, but it's still nevertheless, it's a fundamentally flaw. I don't think any of you would have said Toronto as an answer to that. So that's Watson. I now want to talk about AI and computer games. So this has been a big area of research where AI has been applied, and I want to show you some of the power of sort of machine learning, so the computer algorithm learning how to play the game. So the game you're going to see is called Atari Breakout, which for those of you a certain age, much like myself, may have spent quite a lot of your youth trying to play and trying to master this game. The key bit to know is that the algorithm doesn't know how to play the game. It knows nothing, okay? So it knows that certain actions can be taken. It knows that there's a score that it's trying to make more, to increase. So we spoke about rewards and preferences. So its preferences are for things to have more points than less points, but it doesn't really know how to get those. So this is after about sort of 10 minutes of training. This is somewhat reminiscent of the level I got to, I think. Okay, so it's sort of learning that hitting things back is a good thing, and that when you knock tiles out, you get points, and so that's a good thing. So it's having to learn all of those things. All it knows is the pixels on the screen. So this is after a couple of hours of training. So I got nowhere near this. I don't know if any of you did. That's pretty impressive, I think. But there's more. So after 240 minutes of training, so what it learned is that actually if it could get the ball, if it could construct a tunnel, and it could get the ball up above it and knock things down from the above, then actually it would get very many more points. So that was never programmed into that machine. The people who constructed it had no idea that that was a good thing to do. What would have happened is that in one game, by accident, that would have happened. It would have constructed a tunnel, and it would have learnt that actually that action is a really good thing, and it increases the number of points I get. And then it would have realized that that's a good thing to do, and then tried to aim to achieve that in the future. But that's sort of an example of a machine learning program, not just doing what it's told, it's doing things over and above what it has been programmed to do. Now, sort of the games, the computer games, are a really nice, constrained environment, okay? That you see the pixels on the screen, you have a set of actions that you can take and a set of moves. The real world is very much more complicated than that. So this is what the world looks like to an autonomous car. So it has to try and work out what else is out there, try and classify cars, other vehicles, people, zebra crossings, cars coming its way. And so the real environment is real AI environments are very much more complicated than that. And so sort of what you want to be able to do is to be able to do that similar sort of learning for these sorts of environment. And as you see, it is just very, very much more complicated. You don't know what's coming, you don't know where someone's going to step out in front of you, you're not entirely sure what it is. And this is what it looks like to the car's sensors. So this is, we're looking in the brain, if you like, of an autonomous vehicle. This is what it's trying to do to be able to drive and to make decisions. It's having to make these sorts of classifications of what's going on in the world that us human drivers routinely do. But actually, when you try to get a computer to do it, it's really tough to be able to do. And so sort of what you end up with is a very complicated algorithms and bits of software to try and drive a car. And so I want to sort of show you how that is being addressed. So this is an autonomous vehicle at the beginning of its training. Less impressive, perhaps. But it can start to sort of learn its way around the cones, and so it learns that crashing into cones is a bad thing to be able to do. And after subsequent learning, you'll see them with their hands out the top of the car there, turning corners, steering round paths, seeing construction cones. I think it has a bit of a fixation for cones, this car. I think it's learnt those. Okay, so actually even going off the road on a detour in order to come back. And sort of that's learnt behavior. No one has programmed it to do that. It's got an algorithm inside it that teaches it how to learn, and then it's through experimentation and through simulation, it's starting to learn and starting to be able to exhibit those sorts of behaviors. So I want to talk now about some work that I've been involved with. So this is work that I did in a project called ORCID, and this is about using artificial intelligence to respond to disasters. And in particular, we did this in collaboration with a charity called Rescue Global, who took the AI system that we developed and use it to respond to the earthquake in Nepal. And so what you have in these sorts of in the control room is lots and lots of information coming in from lots of different sources. So some might be from social media, they might be tweets, they might be various other forms of information coming in from people on the ground, bringing in photographs, sending in photographs, and sort of them understanding and then sending some people out and going, actually this building is in a good state, this road has been taken away. So it's got a variety of different information coming into it from a variety of different sources. So some of it is good, high-quality stuff. It's Rescue Global staff who are on the ground and can confirm that, yes, that building over there has been demolished or that's in a state of disrepair. Some of it is social media, which is, in general, a bit less certain about what's going on and its precision, and also the veracity of the information. So sort of we did initial prototyping of this in Haiti, and this is what this is shown in. And actually what subsequent analysis showed was that people in Haiti, when they tweeted into this, actually over-dramatized how bad the state was in their particular region. For entirely good human reasons, you would think that, okay, if I say that this is really bad, we're more likely to be dealt with sooner, and so people will come and rescue us sooner and make our area better sooner. And so you have to be able to cope with that information. And so what the AI system is doing here, or has done here, is bring in all of this information from different sources. Some is pictures, some is media, some is good quality information, some is poor quality information, and has tried to construct a map of what's good and what's bad. That's the sort of heat map, which is what those pictures are there. So sort of the red bits are the bad bits, and the sort of green bits are where things are a bit better. And so here what we have is the AI system combining all of that information together. So the AI is summarizing huge volumes of information, far more than a human could hope to process. Human first responders can also augment this system, so they can add where they know information into it, and then the system will reconfigure itself. So if someone from Rescue Global has gone to an area and taken some readings, then it will feed those things into the system, and it will then update and take into account accordingly. So you've got AI working alongside people, so sort of the first responders working, the AI people are updating their assessments to be consistent with that. And in particular, what that was doing, for the observant amongst you, you will have seen a series of red circles with question marks in the middle. And actually what that was doing was identifying key bits of the city that it was best to go and send either some people or some drones, some UAVs to explore, because they're particularly interesting. And what the system could do to the controller was explain why you should go there. So it could look at the evidence for why it thinks that this is a good system, a good area to go and look at. And as I say, we use this as Rescue Global used this system in Nepal. In particular, they were faced with the challenge of placing water filters within a 50-mile radius of Kathmandu. And so what we did was we crowd-labeled, so we got members of the public to help us over a weekend, and we got them looking at satellite images through an internet platform, and they were able to sort of label some of those. And then we put in alongside that OpenStreetMap building information. That's a bit like Google Street Maps for those who know that version of it. And we sort of combined what the humans were thinking about this with what the machines were thinking about this, and it identified 12 areas that they should go and place their water filters in. Now, 8 of those they knew about. They were the obvious centers of population, so the algorithm is merely confirming where the humans should go. But our system identified 4 areas that they had not thought about and were not aware of. And so what they did is actually they had sufficient trust in us by then. We'd been working for a while, and actually they sent people there. And they were very happy that they'd sent people there. And those 4 that we'd identified that they didn't know were as equally important as the 8. So sort of people's lives were saved here by being able to process information, make sense of it, and sort of augment what the human team would do in terms of where they would go and where they would place things. And so if we go back to our example, we've got a number of areas that are interesting to go and explore. Here we're going to show it in terms of sending a team of drones, so UAVs, flying robots there, in order to explore them. And again, you have that mix of humans and machines working together. So the machine will do some planning or do some initial allocation, that the quickest, fastest way to get to as many areas as you can is to send this UAV here, this one there, and so on. And then what happens is that humans can add their extra information, the extra context that they know that the machine doesn't know on top of that. And they can change that. So they can say, actually, I don't want that UAV to go there. I want that UAV to go there, because they know something about there or that UAV that's in particular. And then the rest of the system adapts to that and reconfigures itself around that. So again, you've got that mix of AI doing a lot of the complicated scheduling and humans adding extra what they know, extra context that's not in the machine or the machine can't figure out on top of that. So using their experience, the first responders determine which teams are best suited to what areas. So they might, in some cases, send multiple UAVs to one area because actually it's really important. So the AI is computing what is the best schedule to minimize completion time, and then the humans are tweaking that. And you could do it the other way around. Okay, so you could start with the humans constructing it and the AI making alternative suggestions to it. It worked either way round. Also, during the course of the plan, you have AIs monitoring that incoming information while the plans are acting and checking that the plans are still valid, okay, that the key areas are still the right key areas to look at. And so you have that continual partnership. And this isn't just sort of just applicable to disaster response, sort of this piece of people working alongside. Here's one of the sort of early examples where you can show sort of a statistical improvement when you add people together with machines in order to do a diagnosis. So this is machine learning, so learning about the system for a particular breast cancer diagnosis. So we had some human pathologists who have an error rate of 3.5%, working on their own. You have the AI model working on its own, which actually does better in this task. I'll come back to sort of the kinds of tasks that AI is good at and how it interfaces with human expertise shortly. But then actually when you put the two together, so when you have the AI model and the study pathologist working together, then actually you're able to get a much reduced error rate. And sort of that for me is, I think that's the sort of canonical example of where we're going to see a lot of AI and where AI is really adding value into these sorts of systems. So sort of that's my tour and introduction to AI, to some of the applications of AI. And I want to sort of in the final few minutes of the talk about AI and its impact on society. Remember, right at the beginning, I spoke about those, or I highlighted those dire predictions from Stephen Hawking and from Elon Musk about what it's going to do, to what AI might do to society. So there have been a number of studies. I've picked one of the first ones from Frey and Osborne in Oxford about the extent to which jobs are likely to be automated by 2030. So sort of they've done a number of predictions of different sorts of jobs and sort of classified them into highly likely to be automated, a medium likelihood, or a low likelihood. And you could sort of see different sorts of categories here. This is but one of many studies. This is a very fashionable thing to be doing at the moment, and lots of authors and lots of big companies are doing this sort of analysis. These are quite high numbers, I think. So I genuinely don't believe that 35% of employers' jobs are at risk of highly likely to be automated, but it's out there. There are some numbers that are bigger, there are some numbers that are smaller. The key thing to note, or there are a number of interesting things to note from this, is it's not just manual jobs that sit in this category. So it's not just low-skilled jobs that are susceptible or potentially susceptible to automation. It's often associated with the amount of routine in a job, and I'm going to give you some high-skilled jobs that could be at risk of automatability in the near future. This is the UK version. If you look at they did the same sort of analysis for different other countries, and that their numbers were even bigger. And it depends upon the sort of mix of jobs that you have going on in your economy. As I say, this is but one example. So here I think are some examples of where high-skilled jobs or things that require highly qualified people to do them are at risk or potentially at risk from sort of AI being involved in them. And I'm trying to be neutral in the way that I describe these things. So we've already spoken about medical diagnosis. So there are a number of diagnostic tasks looking at medical images of a whole variety of different things that actually you can train a machine learning algorithm to be really good at and to be better than humans in the way that they solve it. Not all of them, but there are a number of complex tasks. So, highly qualified doctors looking at images. Actually, you can see a number of examples where the AI systems are able to outperform them in certain cases. We've already seen in the financial trading industry, if you go and look at a stock exchange and look at the floor now, actually what you used to see is lots and lots of people in there merrily trading away. That's now largely disappeared. Trading is generally automated. It goes between computer algorithms that are making trading decisions. What to sell, when to sell it. So again, highly skilled, highly well-paid jobs. Jobs in the legal profession, so things that require legal qualifications to be able to do. So looking back through cases, being able to identify prior art, prior information that's relevant to these cases. Again, a very complicated activity that people require many years of training to be able to do. Again, there are AI systems that can do this well. And also language translation. Again, something that's a very complex activity, very difficult for humans to do. Actually, computers are getting increasingly good and increasingly better at translating between different languages. And so these are all, as I said, highly skilled jobs that are being tackled by AI. A number of these are where the AI systems are starting to outperform or at least get to the same level as humans. So what does that mean for our jobs and our society in the future? So you will have seen, or you may have seen, sort of dire predictions that most of us are not going to have jobs in the future, and we're all going to spend life on holiday, and we need to be paid a basic wage because there's just not going to be jobs around. That's one end of the spectrum, and people are serious and they have debates about that. To be able to answer that question, you sort of have to weigh up the relative balance between a variety of different forces. So the first of these is what numbers of jobs are going to be lost. And sort of technical revolutions and technical improvements throughout history, these are the Luddites, have led to people being concerned about their job and actually being displaced from their job. So I believe that there will be people whose jobs are taken away by AI systems. Okay, so there will be jobs and types of jobs that are no longer relevant anymore. There will be, as there always have been, new sorts of jobs that are created. Okay, so a number of years ago, there weren't many jobs as cybersecurity experts. There weren't many jobs as app developers. Okay, so these are new jobs that the technology has helped create and grow the market of. There will be jobs that are easier, quicker, or cheaper to do. So again, if you go back to the legal profession, I said that a lot of the work that legal clerks do in terms of that sort of initial searching can actually be really enhanced by AI analysis of previous cases. And so you might think that that's led to fewer legal clerks. Actually, what the analysis shows, and this is analysis for the US, is that actually the number of doing that sort of job has actually increased in recent years. And the reason it increases is actually lawyers and law firms are happier to take on more jobs that they might previously not have done because of all the human effort involved. It becomes cheaper, quicker and easier to do a case because actually some of it is now automated. And then there will be jobs that will be augmented. So jobs where a bit of what you do is enhanced by AI, and so it's a part of your activity, but it's not it all. So a bit like the Rescue Global example, some of those activities used to be entirely manual. Some of those are now automated, and it's the partnership of people working together. And so your answer to the question of what is AI going to do for jobs in the future depends on what you think are the dominant forces in that set of equations. And the truth is nobody knows, because it's the future, and predicting the future is a very difficult thing to do. People have opinions about those things, and my opinion is that actually I think we are not going to move to a society where very few of us have jobs. But that's just my opinion, and that's my best guess. Other people very much feel that the jobs loss was going to be a huge enormous piece of this, and actually the rest is going to be small. So it depends on your perspective on life, I think. So to wrap up, so rises in processing power, memory, and data availability have let us solve problems that we couldn't previously tackle. AI is essential for many of these complex problems. There are a wide range of impressive applications for narrowly defined tasks. Artificial general intelligence is some way off, despite what you see in the movies and despite the dire predictions. General artificial intelligence, as you see it in the movies, is not going to happen anytime soon. I think we should think of AI systems as being partners with us. And this leads to a rise in the humans as well as in the robots. And research is needed very much to make machines better partners. They are still often frustrating tools, unable to cooperate and unaware of their social context. Thank you very much.